Good morning and welcome to our special day LCF developers join with ESP on May for the May 2020. My name is Yasaman Qadar and I'm one of the organizers of this training series and also a member of ALCF Performance Engineering team. These webinar series are created to foster discussion between the software and hardware developers of the early users of that technology. Today's topic is UPC++, an asynchronous RMA RPC library for distributed C++ applications. And we're pleased to have with us Amir Kamil. He's from University of Michigan and Lawrence Berkeley National Laboratory. Amir is a lecturer in electrical engineering and computer science at the University of Michigan and a computer science engineering at Lawrence Berkeley National Lab. He earned his PhD in computer science from UC Berkeley, and prior to joining the University of Michigan, he was a postdoctoral scholar and lecturer at UC Berkeley. Prior to joining the University of Michigan, he was a lecturer at UC Berkeley, and he remains affiliated with the computer language and system software group. His research interests include compiler analysis, optimization, and programming models for high-performance computing, diversity and inclusion in computing, and software tools for computer science education.
Thank you, Yasaman, for the introduction, and thank you, ALCF, for hosting this session. So I'll start with just a brief acknowledgement of everyone who's contributed and collaborated with the project. I do have to apologize a little bit. I noticed that there is a 3 or 4 second delay after I switch the slide before it actually shows up. So I'll try to be mindful of that. I'll also mention that I do see the chat as well, so I'll also be paying attention to that as well. But as Yasaman said, if you have a question, when I pause for questions, which I'll be doing quite a bit of, feel free to unmute yourself and ask. The UPC++ library, sort of the motivating applications are irregular applications that have irregular data structures or irregular communication patterns. So this includes things like sparse matrix methods where the number of non-zeros is irregularly distributed. Adaptive mesh refinement algorithms where the resolution of the grid is is finer or coarser at different areas. And also problems that are inherently irregular, like graph problems, distributed hash tables, and we'll actually see a little bit about distributed hash tables later today as well. So most common amongst these applications is that, again, the data is distributed irregularly, but also the processes communicate different amounts of information to each other. And this amount can be data dependent. It can be dependent on the input data. It can be actually dynamic throughout the application. So for instance, many AMR applications actually will end up coarsening or creating finer grids as needed. So what we need is a programming model that essentially supports these sort of irregular communication patterns. At the same time, we also see system trends that are sort of encouraging or leading to fine-grained communication. So we have exascale systems like Frontier appearing very soon, and we have applications that are supporting fine-grained communications like the one that we talked about. And in this fine-grained communication, we have an overhead term as well as sort of a bandwidth term as well. And so on these newer systems, the latency is improving much more slowly than other things like bandwidth or computational resources. And so the overhead term ends up dominating the communication time. And so we end up with applications that end up being latency limited. Another thing that we're seeing with these new systems is that memory per core is also dropping as the number of cores increases. And so this means that applications often have to do more communication rather than replication of data. And so again, this is another system trend that encourages or that leads to more fine-grained communication. So in order to address this, there's a few things that we kind of need to do on the programming model side of things. The first thing is that we need to support asynchrony. So the ability to overlap multiple communication operations or communication with computation so that we can, hide some of this latency. The other thing that we need to do is we need to minimize the overhead term, because again, that for many of these applications is the dominant term in the communication. So, one of the main ways of doing this is to essentially simplify the communication model so that we allow each processor to actually directly access memory on another process, so that essentially the initiator is the only one that needs to actually be directly involved in the communication. And so we get a number of benefits from this. We don't need to go through the process of matching sends and receives, neither in the application itself, but also underneath in the communication library as well. We don't need to guarantee any message ordering, so we don't have to essentially do tag matching or anything underneath in the library to ensure ordering. And this also means that on the application side of things, there aren't unexpected messages. Because again, the target essentially doesn't need to participate directly in the message itself. So, if it receives a message that, some other process initiates it, it doesn't actually need to worry about that happening at an unexpected time. So, this communication model is one-sided. All the metadata is provided by the initiator rather than being split between a sender and a receiver. And, programmatically, it looks a lot like shared memory. So it's also a somewhat more familiar programming model as well. And one of the things that makes this a good fit for large-scale systems is that we have modern network hardware actually provides the ability to do remote direct memory access. Okay, so again, initiating a message on a sender, a put or a get at the initiator, and then having that actually go to the target and access the data without involving the CPU at the target. Also, if it so happens that the target happens to be addressable through just direct memory access rather than going through the network, then the library can also essentially compile that away to a load store to avoid the overhead of going through the network layer. Just to illustrate sort of what kind of gains that we could get from this programming model, and also to motivate our choice of using GASNet-EX as our underlying network communication library. We have some results here that are comparing GASNet-EX to MPI3 RMA. Now, both of these are using the one-sided model, but again, we have GASNet-EX as one implementation of that one-sided model, and we have MPI3 as a different implementation. What we see on sort of these results over here is comparing both puts and gets on GASNet-EX versus MPI RMA on 4 different systems. 3 different actual software implementations of MPI and 2 distinct network hardware types. And on all of these, we see that GASNet meets or exceeds the performance of MPI3 RMA. And the improvement between GASNet and MPI is between 6 and 55% for put latency, 5 to 45% for get latency. And we also have better bandwidth results as well. And so here's an illustration of the bandwidth numbers, and we won't go into details in this because this is a UPC++ talk, not a GASNet-EX talk. But one of the things I want to point out is that particularly sort of for intermediate message sizes, we see that that GASNet does better than MPI. This is a direct comparison between GASNet-EX and MPI3. Of course, UPC++ is a library that's built on top of GASNet-EX. So the next question is, are these numbers reflected once we add the UPC++ layer on top of that. And in fact, we see that we have similar results for UPC++ compared to MPI directly. Okay, so again, we see that particularly for intermediate messages and also for smaller messages as well, we have lower latency for UPC++. And on the bandwidth side of things, we see that, as we saw with GASNet, intermediate sized messages get higher bandwidth for UPC++ compared to MPI. Again, what we have here is we have one-sided communication, and the core programming model in terms of memory that uses one-sided communication is referred to as the Partitioned Global Address Space model. And so what we have in this model is that we have storage on each process that's globally visible to the other processes so that they can actually access it directly. We have, each processor also has some private memory as well, so things like stack memory. In the UPC plus model, we actually have a distinction also in heap memory between the portion of the address space that is private and the portion that is shared. And another thing that, another sort of fundamental aspect of this programming model is that it separates synchronization from data movement. And again, because it's one-sided, it doesn't actually require both the initiator and the target to participate directly in the communication. That means that there isn't an implicit synchronization when it comes to the communication as well. And so, this decoupling means that, for instance, if we don't need that synchronization, we don't need to pay the overhead of doing that. And on top of that, if we have multiple pieces of communication, we can actually amortize the overhead of synchronization by just doing a single synchronization for a group of messages rather than, for a group of transfers rather than doing one for each one. Now, this PGAS model is not a new model. It's been around for over 20 years. We've had many different languages and libraries that support this. So sort of the first generation was UPC Titanium, CoRA Fortran. And then, we sort of had the next generation languages, including Chapel and X10, that support the PGAS model. And then more recently, we have a lot of work in terms of libraries for using the PGAS model, primarily implemented in C++. So this includes UPC++, includes CoRA C++ as well, Dash, and several other libraries that are implemented in C or C++. Of course, this presentation is about UPC++, so that's what we'll be focusing on. Questions so far?
In these tests, what kind of problems have you been solving?
So we will talk about some application examples at the end. But some of the work that has been done in UPC++ includes sparse solvers, distributed hash tables, and also larger applications that actually use that as part of its component. So we'll talk about MetaHitmer, for instance, which is a full-featured genome assembler, assembly library. And, there have been several other sort of projects that have used UPC++ directly. And of course, as far as UPC and Chapel and the other PGAS libraries, there's a much larger area of work that has used those. So far, we've talked about one-sided messages. We've talked about the PGAS model. We'll actually look in a little bit more detail in terms of how the PGAS model is actually structured. But one thing that I want to do before that is I want to make clear that PGAS is the memory model. And the memory and the communication model. It's not the execution model. The execution model is actually an orthogonal piece of the programming model as a whole. UPC++ in particular uses the single program multiple data execution model, which, if you're familiar with MPI, is the standard model used in MPI. Other libraries use other models. So, for instance, Chapel and X10 use more of a task-based model as opposed to SPMD. So, what we have in the SPMD or SPMD model of execution is that you have a fixed program that is run by each of the processors. Now, the processors don't run the code in lockstep, but there are synchronization points. And we have one here in the form of a barrier. Okay, so essentially at startup, all of the processors will first call the initialization of the UPC++ library, and then they each print out a message saying hello from their rank number. Okay, so at the bottom we actually have a visualization of this execution. These prints, again, they get executed concurrently amongst the processes. There's no ordering guaranteed between them because there was no synchronization yet. Then we have the barrier. And so this does synchronize all the processes. What the barrier does is it prevents anyone from proceeding until everyone has reached it. Okay. And then finally, we have one more printout specifically from process number 0. And so that one is synchronized with respect to the previous printouts because of the barrier in between them. And then finally, we have the program end. So question, UPC++ is an API, not a plugin. So as Dan helpfully mentioned, it's a C++ library. So it's built using standard C++, and we'll see more details about this later. But it's essentially, you can install it and pound include it as you would just as any other third-party C++ library. Again, just to summarize, we have the memory communication model, which is PGAS. We have the execution model, which is primarily SPMD. So going back to the memory model and just looking at it in a little bit more detail. So again, it's the partitioned global address space model. So there's two pieces to that. There's the global address space part, and then there's the partition part. So as far as the global address space part, what we have is a conceptual conceptual global address space, which is a collection of shared memory segments across the processors. So if you look at the bottom, you can see an illustration of this. We have the memory for each process is divided into a private segment and a shared segment. The collection of those shared segments is the overall global address space. Okay, and so each process can access its own private segment, its own shared segment, but also the shared segments of the other processors. And because we have this global address space being constructed from these different shared segment partitions, that's where the partition part of the nomenclature comes from. Now, when we actually create an object in memory, it's created in some partition of this global address space if it is in the global address space. And so when we obtain a pointer for that, we have something called a global pointer, which includes both the memory address as well as sort of which process created this particular object. So that's encapsulated in the pointer abstraction itself. We'll talk about this more in just a moment. But because we have this sort of affinity encoded in the pointer itself, that means that the library can actually provide a means for reading the pointer, which underneath the hood goes out to that process and actually obtains it using one-sided communication. And another thing is that the pointer also gives the programmer a means of actually programming for the locality. So I can actually check, is this something that I can access directly versus is this something that I need to access through a one-sided message. So a little bit more detail on global pointers. A global pointer is a pointer that can points to something in the global address space. Now that object may actually be in the local process's memory. So for instance, over here, in this illustration, we have both local, just basic raw C++ pointers, as well as global pointers. And I'm actually distinguishing in between them both by color as well as thickness. We have a local pointer, which again is just a raw memory address, and then the global pointer also includes an affinity, so it's a little bit larger. So I'm illustrating that with this extra thick line. So here on process 1, we see that we have a global pointer that is actually pointing to an object that is in process 1's memory. Okay, so this in this case, it happens to be a local object, and process 1 can actually convert that to a raw pointer and access it through the raw pointer if it wanted to. On the other hand, on process 0, we have a global pointer that is actually pointing at the same exact object, which happens to be located in process 1's partition of this global address space. Now, global pointers themselves, just like local pointers, they can live in the private segment or the shared segment. It's just another object as any other C++ object. But again, what they refer to has to be something that lives in the global address space. Okay, so just to illustrate this, essentially what we have, the data structure that's being represented here is a linked list where the elements are actually divided amongst the processors. So we have these next pointers in between the nodes of this linked list. So again, that illustrates these global pointers also living in the global address space as well. So questions so far? I see a few in the chat. Does one need to link UPC XX, or is it header only? It's, as Dan mentioned, it's not header only. And we will talk a little bit about sort of how to build a UPC++ program using some of the front-end scripts that we provide. By the way, I'll just mention, because Yasman didn't get a chance to introduce the entire team, but we do have a few other team members that are participating in the chat, and like Dan, helpfully answering questions, and Paul Hargrove as well. So, take those answers as official. So, can we give some examples of using this? We'll get to that. So please bear with us before that. Are the global pointers available to provide communication optimizations for integral types that dist object may not provide because dist objects are classes or structs? So I suggest we hold off on that question since we haven't actually talked about dist object yet, and it's actually going to be a while before we do that. And we'll kind of see that there's a distinction between what the two things do. A global pointer is just something that references memory located on a different process. A dist object is actually a more complex data structure that is used for essentially representing a very simple form of distributed data structure. Okay, and so we'll see more details about that later. Other questions? Like X10, XP, UPC++ follows the PGAS model. Is this true? I have the feeling that X10 is much more task-based. So I wouldn't say that the programming model is exactly the same, but both of them do have asynchrony. So the X10 model is essentially task-based at its core, whereas UPC++ is SPMD with tasks on top of that in the form of remote procedure calls. Okay, so hopefully it will become clearer as we get to talking about RPC. We haven't talked about remote procedure call at all yet, but we will get to that. So questions, why would global pointers be larger than normal pointers in principles? 64 bits is not enough. So that's an implementation question. If you could imagine an implementation that, for instance, reserves, 48 bits for the actual memory address and 16 bits for the process number. You'd have to ensure that on the system that your actual virtual address space fits into those 48 bits. So yeah, it's an implementation question. Conceptually speaking, though, regardless of the implementation, we have a global pointer as a combination of a local memory address and the affinity. Other questions? How is the address space partitioned? So again, just going back to the previous slide, we see that, there we go. We see that it's constructed of segments that are on the individual processes. So those are the partitions of the global address space. How is it partitioned between global and private memory? Upon UPC plus initialization, what we have is that there is actually a segment that's reserved for the shared segment. It's not. It's a different segment in our implementation than sort of the standard C++ heap. Let's go ahead and move forward. In terms of the actual programmatic abstraction, as pointed out, essentially we do have this abstraction of a global pointer, and since we're a C++ library, it's actually a C++ template. It's parameterized by the object type. Okay, so essentially this is the global pointer equivalent to a double star. And we have global pointer of double. And again, what we have underneath the hood is we have both the memory address, where that object is located in the address space of the process that created it, as well as the identity of the process that created it. In terms of UPC++ itself, so far what we've talked about is not unique to UPC++. As pointed out, there are other models like X10 and Chapel, Co-Ray, Fortran that provide some of these aspects, particularly when it comes to the PGAS model. So what UPC++, how it's different is that it's a compiler-free approach. Okay, so entirely library-based using standard C++, and in fact we rely solely on C++11, though we do support later C++ versions if an application wants to use, say, C++11 or 17 or even 20. The library itself, again, built using standard C++, but on top of the GASNet-EX communication library in order to provide low overhead communication. And so we already saw numbers comparing GASNet-EX to MPI3 for micro benchmarks. So that's sort of one motivating reason to use GASNet rather than, say, MPI3 RMA or some other one-sided communication library. But another thing that's really important for us is, as we'll see momentarily, one of the key features of the UPC++ model is a remote procedure call. And GASNet actually provides active messages that allow us to support this very efficiently. And so that's something that we don't actually see in other models like MPI3. The GASNet developers who are with us today, again, Dan and Paul, have done an extensive amount of work to make sure that it's a portable library across laptops to supercomputers. So they do the hard work in terms of making sure that the underlying communication and active messages are efficient and tailored to each different system and network, and then we take advantage of that in UPC++. Now, another thing that we get out of a compiler-free library approach is that allows for easy interoperation with existing programming systems that also support, C or C++ bindings. So, one of the other things that has motivated us on the programming model side of things, in terms of, for instance, using the SPMD model, is that it also, again, makes for easier interoperability. So because both UPC++ and MPI are built on the SPMD model, that means that it's relatively straightforward to actually build hybrid applications that use both. And in fact, there are many examples of applications that use both, including two of the application case studies that we'll see at the end today. And also, just like MPI can be mixed with on-node threading libraries, UPC++ can be as well. We've talked about PGAS and one-sided messaging. And I will mention that we often use the term RMA to refer to this. So that's remote memory access. And so this essentially means one-sided put and get. And I will clarify that RMA and RDMA are two different things. We talked about network hardware supporting RDMA, remote direct memory access. So that's a feature of network hardware, whether or not underneath the hood, the network actually supports one-sided communication that doesn't require the CPU to be involved in. RMA is the programming model. And we can have the programming model without having network hardware support for it, and vice versa as well. Okay, so regardless of what the network hardware provides, through using GASNet and the abstractions there, we actually support a one-sided programming model, regardless of what there is in the network. The other main feature of UPC++ is remote procedure call. Okay, so RMA is low overhead, just movement of data. RPC extends that to moving computation as well. Okay, so for many fine-grained applications, it's actually useful to move work over to a different processor rather than moving data over. We have several different design principles that went into designing and implementing UPC++. So one thing that is perhaps different from models that like UPC and Titanium is that communication is syntactically explicit. And the motivation here is that we don't want to be hiding any communication. Communication is expensive, and we want that to be visible in the programming model so that we encourage performant programming as opposed to encouraging non-performant, non-scalable implementation. Another important design feature, as we'll see, is that everything in all communication in UPC++ is asynchronous. Okay, so if I do a one-sided communication like a put, that doesn't actually wait until it completes before I actually can move on and do something else. So instead, I get I can work with it through abstractions like features and promises, so that I can actually the application can do something else while that communication is happening. And finally, both the implementation as well as the abstractions, the programming abstractions that the library provide, are designed to be scalable. So this means that we avoid unnecessary replication. We look at underneath the hood, both at the GASNet-EX level as well as the UPC++ internal data structures are designed to avoid are designed to essentially use a sublinear memory per process as the number of processors scales. And also abstractions we provide, such as distributed object, which has been mentioned, but we'll see in detail later, are designed to essentially avoid unnecessary replication. Okay, so let's look at just a little bit more in terms of what we mean by asynchrony. Essentially, when it comes to a communication operation, we have an initiation of that, and that's separate from the actual wait for completion. So if we look at the example here of some code, we have a one-sided get from a global pointer. Okay, so again, this global pointer may be referencing memory on some other process. We do an arget of that. What we don't get back, we don't directly get back this actual data value, which is an int. Instead, we get back a feature. And we'll talk about what a feature is in more detail later on. The important thing for now is that essentially what we have, rather than waiting until the transfer is completed, we essentially get a handle to the result. And so this allows the application to actually do some unrelated work while that transfer is actually happening. And then eventually, when the application actually needs that piece of data, then it can actually do a wait. And so this wait will wait until the transfer is completed. If it's already completed, then great, we just get the value directly. Otherwise, the program waits, and it is making progress underneath to the internal state of the library, which is something that we'll talk about later while this is happening, until the transfer completes and we get the value back. So I mentioned remote procedure call being a key part of the UPC++ programming model. And so what that looks like is essentially we're executing some function on another process. And so the way that works is we first initiate that with a call to RPC. We refer to some target function, which can be, just a regular C++ function. It can be also a function object that overloads the function call operator. It can be a lambda as well, for those of you who like C++ 11 lambdas. Sorry, I pointed at the wrong thing over there. The first argument is actually the target process, and the second argument is actually the function to be executed over there. And then we have whatever arguments that function needs when it's invoked. Okay, so this is what the initiator does. And again, it's invoking this on some different target process. And so then what happens is that the library actually, does a transfer of the arguments as well as a handle to the function. It enqueues the function on the target to be executed. Then at some later point, at the target will actually execute the function on the arguments that have been transferred. And then the result, it becomes available to the initiator by the future. Okay, so the return value of this RPC is not the return of the target function. It's a handle to that result in the form of a feature. And then later on, when the function actually executes and the return value becomes available, that gets transferred back from the target back to the initiator, and the feature becomes ready and for the value to be read out of it. And again, just like one-sided messages, this is asynchronous. So this means that we can have multiple RPCs active concurrently, allowing us to hide the latency of any particular call. Questions on this? Can UPC++ run independently of MPI and or OpenMP? Can you clarify what you mean by independently? So you can have an application that, can it run, I see, got it, without needing them. Yes. So UPC++ is a standalone library. It doesn't require MPI or OpenMP. It can interoperate with them, but it can also run, they can also be used without using MPI or OpenMP at the same time. Other questions? All right, so now let's dive into the nitty-gritty details of the library. So far, again, we've concentrated on the programming model and the high-level features that the programming model supports. Now we're actually going to get into the details of how to actually use it. So as always, we'll start with Hello World. Now we've actually already seen sort of a version of the Hello World when we were talking about the SPMD execution model. So just a reminder, in the execution model, all the processes will run, we'll call main. Okay, so it's C++. We include both, standard library headers as well as the main UPC++ header over here. Okay. And then once we've pound included the UPC++ header, we can make calls into that namespace, into the UPC XX namespace. So the first thing we need to do is initialize the library. This is similar to MPI init if you used MPI. And so this sets up the UPC++ runtime. Once the library has been initialized, now we can actually call into UPC++ to do other things. Okay, so we have the rank me call gives us the rank number in the of the calling processor, and rank n gives us the number of processes. Okay, so here we have a hello world from process I out of N. Okay, and so what we see down here are the outputs. And again, we don't have any synchronization here. There aren't any barriers or anything in this piece of code. So, there aren't any ordering guarantees when it comes to these outputs. And in fact, on some systems, these printouts can actually be interleaved as well. And, when we're done with UPC++, just like MPI, you call finalize to tear down the library and release its resources. So question, is there an RAI method for initialization and finalization? Good question. I don't think we actually support one directly. So no, we don't actually have it directly, but it's, of course, trivial to implement yourself, just by defining a class with a constructor and a destructor. Other questions? All right, for those of you who would actually like to try this out, the code itself, there's several code examples that are available through the URL that was at the beginning, and I will request Dan to repeat the URL in the chat if you can. But this is a URL to our training materials. So you can actually, download those and run them. And if you want to try these out on the various clusters at the various supercomputers at the DOE centers, we have installations on ALCF, NERSC, and Cori using by doing module use and module load commands. There's more examples and information about how to use UPC++ on all three of these centers available on the UPC website. You can also download it itself and install it on your own computer if you would like to. Again, we support everything from laptops to supercomputers. As far as actually compiling and running UPC++, once you've either installed it on your own computer or module loaded it, we provide some front-end wrappers for convenience, just like MPI installations tend to do. So we have a UPC XX compiler wrapper, which invokes an underlying C++ compiler with the right arguments. Okay, so with the right -I to get our headers included, and -L to get our library linked in as well. And just like a standard C++ compiler, you pass it the source files and can give it a custom name for the resulting executable. We also provide other mechanisms if you want to invoke your own compiler directly. So there's a UPC XX meta script that actually you can use to extract the necessary arguments for invoking your C++ compiler directly. And we also have CMake integration as well. So that's what you use to actually compile a UPC++ program. And again, it's C++ plus our library. So it's just invoking the normal C++ compiler underneath the hood. We also have a launch wrapper as well, UPC XX run. So this is similar to MPI run or MPI exec, which wraps the sort of on many of our common systems, whatever launcher is used over there. So srun, AP run, or whatever the platform supports. So it provides essentially a standard interface on top of those. Okay, and so here we are launching a UPC++ program with 4 processors, and the program itself is the hello world that we just compiled. So can you repeat what is UPC XX meta? It's a tool for extracting the arguments that need to be passed to the C++ compiler for compiling a UPC++ program. Okay, so UPC XX invokes the compiler directly. UPC XX meta doesn't, but it gives you back the arguments that you should use to invoke it yourself. Again, thank you, Paul and Dan, for putting links in the chat. Again, several of the examples that we have in the slides are actually available through that link, and you can download them and try them out yourself if you would like. So let's now actually look at the library APIs directly and the different features that the library supports and how to use them. And so we'll start with RPC. Okay, so remote procedure calls. And just to sort of address the questions that was asked earlier in terms of X10 versus UPC C++, the programming model. So X10 again is primarily task-based and essentially has things like RPC, but starting with sort of a single task, whereas UPC++ starts off with the SPMD model, and then you can do any of those processes can do RPC to invoke code on other processes. So it is a little bit of a different programming model, but with some similarities as well in terms of supporting remote invocations. So let's look at this example over here. So we have this simple area function that just takes the arguments and multiplies them together. It's not doing anything interesting. It's just here for illustration. And in a real application, you'd be doing something more interesting in the function that you want to invoke somewhere else. Okay, so that's the function that we want to invoke. And what we want is we want process 0 to actually invoke this on some other target process P. Okay, so what process 0 will do is it will invoke RPC on the target process. So the first argument is the target process. The second argument is the function to be invoked. So here we have area. And then we have whatever arguments we want to that function. So some A and B over here. Okay. And before I go further, neglected to mention this earlier, so I'll mention it now. Just a note about the convention in the slides, which is that for UPC++ library names, our convention is to color them in red and underline them, just to make it, hopefully more obvious what things are UPC++ as opposed to, say, standard C++. Okay. And I've elided the UPC XX namespace here just for space. But again, that would be essentially equivalent to just doing a using namespace UPC XX or a using UPC XX : RPC. Okay, so again, here we have the invocation of the area function on process P. So as we talked about before, what that does is it actually transfers over the arguments themselves. They do actually get transferred over. As far as the function, we don't actually transfer the code. And that's because, we have the SPMD model. All the processes are running the same code image. So there is an area function on process P. It's the same function, right? Because we have the same executable. So we don't transfer any machine code. Instead, what we do is we essentially construct a handle to the area function, and that's what gets transferred. And so pictorially, I've represented here as like area in quotes. Okay, but I don't actually mean the string area. I mean there's just some sort of handle that we create underneath the hood that actually gets transferred over. So question, should A and B be global pointers and area have those as arguments? So you could do that if that's what you wanted, but that's not what we're doing over here. Okay. So here what we're doing is we're transferring the arguments A and B directly, which are ints. And those arguments are operated on directly on process P. And then the return value is directly transferred back to process 0. Okay, so we don't have any notion here of sort of global pointers or doing one-sided transfers. Okay, so again, here we're talking about remote procedure call, not RMA. But A and B live on process P. So A and B are integer objects that live on process 0. They get transferred as part of this RPC, right? So this is actually invoked on process 0. We have essentially pass by value over here. So those int objects actually get serialized into bytes and then transferred over to the target process P. Okay. Are there issues with, I suppose, this address space randomization if the underlying function is compiled into a shared library? So we do some tricks underneath the hood to deal with address space randomization. I don't know the details of how that works with respect to shared versus versus dynamic libraries. But yeah, we do actually do a translation underneath the hood to account for address space layout randomization. Are A and B transferred immediately, or could they be modified before they are actually transferred? So here A and B are passed by value to this RPC function. Okay, so just like with any other pass by value invocation in C++, the value gets read, and then it doesn't matter what happens to those variables afterwards. What is the point in executing area on process P if all the data is on process 0? So that's a good point for this particular example, which again is a trivial example of just multiplying two things together. But typically what you'd want is an RPC that actually accesses something on process P as well. And so really, one of the main reasons to use RPC is to actually avoid needing unnecessary transfers of data. So to move computation rather than data. So here we haven't seen that in this example because, again, it's just a simple example to illustrate what happens for an RPC. Would using address of area produce the same effect? Yes, it would. That's more of a C++ question. So C++ does automatic conversion between functions and function pointers. Here we do have a return value so that that return value does get transferred back to process 0 after process P executes area. Okay, so whatever the product A times B is, it will get transferred back to process 0 once the function has been invoked. So let's take a look at an example of actually doing RPC. And again, we're doing simple examples to illustrate library features as opposed to something that I guess fundamentally would require RPC. We will see later on examples of more interesting things when it comes to using RPC. Okay, but for now we'll stick to simple examples just to illustrate the concept of an RPC and what happens. So here what we've done is we've rewritten hello world. Our reminder, in our initial version, we didn't have any guarantees about ordering because there was no synchronization. This version actually does guarantee ordering. And the way it does that is essentially we have a loop over the process numbers, and essentially the processes take turns doing an RPC over to process 0 with their hello world, and there's synchronization before moving on to the next iteration. Okay. So what do we do in terms of the RPC? So here we're invoking RPC. The target is process number 0. So we're having all the printouts happen on the same process just to make sure that they aren't interleaved by the system. And then what we're actually passing in is a C++ lambda function. Okay, and this is actually more typical, I would say, of C++ 11 programming as opposed to using function pointers. Though you can do either. You could write this as a top-level function and then pass the name of the function. Okay, so again, here we've used an anonymous function, a lambda function. For those of you who are unfamiliar with the syntax, it looks like a normal function definition, except for we don't have a return type at the beginning. There is a way of putting the return type at the end, but it's not super common. We don't have a name because it's anonymous. We have the square brackets here, which is the capture list. This is what pieces of data need to be captured from the surrounding local environment. In this case, we don't need anything, so it's empty. We'll see an example or two later where we actually do have a capture list. Then we have our function arguments. In this case, we just have the rank number of the process that's initiating this RPC. And then we have the function body. And within the function body, we have a printout taking in the rank number, which is being passed as the argument. Okay, so again, we have this lambda function is the function to be invoked on process 0. So that's the second argument of RPC. After the function argument, we have the arguments to that function. So we have, again, the arguments to RPC are target process number, function to be invoked, and then the arguments to that function. Okay, so here we have a single int argument, and we're passing rank me. Again, the process number of the initiator as the argument to that. Okay. And then, as we mentioned before, everything is asynchronous, so we don't actually, by default, it doesn't wait till the RPC is completed before the RPC invocation actually returns. In order to wait, we actually have to explicitly call wait. Okay, so again, initiating an RPC, then waiting for it, and then doing the barrier afterwards, and this ensures that everything is synchronized correctly. Are there lifetime issues with passing stateful lambdas as a capture by reference? Is there a requirement that the lambdas are captured by a value to ensure lifetime management? So again, this is a pitfall when it comes to C++ in general. Right? There isn't anything specific about UPC++ that makes it more or less, essentially, other than the asynchrony part. So yeah, capturing by reference is something that you should be very careful about when it comes to a lambda function. In the UPC++ case, keep in mind that we're doing a transfer to something else. So if I have a reference, it's not going to be valid on the remote processor. And so that's sort of an additional pitfall to capturing by reference on top of just standard C++ lifetime issues. Okay, so we have lifetime issues, and then we also have, is the reference actually meaningful on the remote? And that would not be the case. Can MPI world be exposed? So are you referring to the sort of world communicator? Okay. We have, in UPC++, sort of the abstraction that we have that's similar to a communicator is a team. And the operations that we're doing here are on the world team. So this is including everybody. But we will actually talk a little bit, we will reference teams. We won't actually have a chance to talk about them in any detail today. But we do have support for subset teams similar to MPI communicators, and you can get rank numbers with respect to those smaller teams as well. Without the weight, would it have the same effect in this particular example? So you do need a weight somewhere to ensure that the RPC completes. Okay, so essentially one of the restrictions on finalize is that all outstanding operations have to be completed before, semantically speaking. So you do need a wait somewhere. Here we have the wait before the barrier to ensure that the next RPC doesn't get initiated before the previous one completes. Okay, so again, synchronization is something that we have to do explicitly if that's what we want. In the normal case, we would actually want RPCs to be executing concurrently, so we wouldn't, have the same synchronization over here. Do RPC calls register on other, assuming processing elements? So an RPC can target a different process. So if you have one process per processing element, then you'd be able to target any other processing element. Now you don't necessarily have to have one process per processing core. Again, we interoperate with things like OpenMP, which you can use if you don't want to actually have the abstraction of one process per processing element. Are RPC calls tracked across PEs? I'm not quite sure what you're asking over there. Can you clarify? So there's no RAII on RP. So is there a queue that P is expected to empty over time for RPCs? So essentially, I interpret your question as a question about in terms of progress of actually running these. That's something that we'll come back to later. Yeah, thank you. So there is no RAII on RPC result. No, well, actually, that leads into the second discussion. So let's the next discussion. So maybe hold off on the question until we talk about the next thing, which is what do we actually get back from RPC? And so what we get back is something called a future. And this is a common abstraction in asynchronous programming. It's not unique to UPC++, though there are specific aspects of UPC++ features that, maybe a little bit different than other systems. But essentially what we have is a future is a representation of a computation that may or may not be complete. Okay. And the future itself has a wait member function that you can invoke on it, which will, essentially wait for its completion before returning. Okay, so that's where the wait call is coming from. So what we get back from RPC and actually any other communication call, like as we'll see, one-sided put and get, what we get back is we get back a future that represents the completion of this operation. In this particular RPC, this is the same one from the previous slide, we don't have a return value. And so we don't actually get a value as the result of the RPC, but we still get a completion event that essentially tells us this RPC actually did finish. Okay, so our future is actually a template. In this case, it's empty because we don't have a value, but we still have a notion of, did this operation actually complete? Okay. And then again, we can call wait on it to wait until the completion has happened. So in terms of going back to the previous question on RAII, no, there isn't any sort of, if this feature is destructed, does it actually wait? And that's because, as we'll see in a moment, this feature is actually just a handle. It's essentially a reference to some asynchronous operation. You can make copies of the feature, so therefore, essentially, we can't rely on RAII to actually do the wait. And I'll also mention that just as a design principle, one of the things that we talked about before is we want things like communication and also synchronization to be explicit. And so we don't want to hide those things in a destructor. So a little more detail on what a future actually is. Again, it's a handle to some data structure that tracks an asynchronous operation. And so this data structure is essentially what it keeps track of is whether or not the operation is completed. So it has a ready bit essentially. And then whatever values that are the result of the operation. Okay, so in the case of the empty future from the previous slide, essentially we wouldn't have any data here. We would just have the ready bit. But in this example over here, where we have a feature of int, then we actually have an int data value over here as part of our data that's being tracked, of our data structure for this asynchronous operation. Okay, so the feature itself, it's not sort of the result of the operation, but rather it's a proxy for it. And what the wait method does is it waits until the operation is completed and then gives us the actual result of the operation. Now, this sort of pattern of creating a feature and then calling wait on it is one way of actually waiting for completion. And in fact, we wouldn't typically want to do it immediately. We would want to overlap other things. But there's also, we'll see later, that there's also ways to attach callbacks to have some operation execute on the result of this operation when it's available. And so we'll see that later on. So it sounds like feature corresponds to an MPI request. I would say that a feature is much more powerful than that. And again, part of it is, as we'll see with the then method later on. So we'll see that we have the ability to actually construct entire dependency graphs using features, which as far as I know isn't something that you can do with the requests. So again, typically we wouldn't want to just initiate something and then wait on it immediately, because we would lose all the benefits of asynchrony. And instead, we'd want to overlap multiple communications or communication with computation by doing something in between the wait and the initiation. So in this example over here, what I have is I actually have a vector of features that's going to represent features for multiple communication operations. And then the code itself will initiate a bunch of these operations, so doing RPCs to many different processes, and then storing those features in this vector. And again, notice here what we're doing is we are launching a bunch of these RPC operations before calling wait on any of them. And then afterwards, the code actually does a wait on each of them individually to ensure that they've completed. Now, this isn't the best way of doing this. This is just an illustration of, we can actually launch multiple operations and have them operate concurrently before waiting on any of them. We'll see better ways of actually waiting on groups of asynchronous operations later. So how are exceptions handled? The simple answer is they aren't. So RPC in particular, one of the preconditions is that the function invocation does not produce an exception. And that's because exceptions do not compose well with asynchrony. So let's look at an example, sort of micro benchmark for looking at further UPC++ features. And so the example that we'll look at is a 1D 3-point Jacobi in UPC++. So this is a one-dimensional nearest neighbor computation using UPC++. We have a the global domain, data domain. In this case, we have 12 elements, and then they are divided up amongst 3 processors. So 4 elements per process. Okay, now in terms of the data representation, we will also have ghost cells on the boundaries. Some of the variants we'll look at won't actually use those ghost cells, but they will be present in all of our variants. Some of them will use them. Okay, and again, because we have a nearest neighbor computation, in order to do, and here we'll also have a periodic boundary condition. So in order to actually compute the new value of this grid cell number 1 over here, we need the old value of the neighboring ones, the 2 and the 12, across that periodic boundary. Okay. So the computation itself, again, is just a simple nearest neighbor update. We have the new value of this grid element at index I is computed from the old values at I minus 1, I plus 1, and also the old value of the element itself. Okay. So we're doing a Jacobi iteration. So this is going to be an out of place computation. We have, again, we have the new grid and we have the old grid. So the way this code is going to work is it's going to use two different grids, and it's going to essentially rotate between them in terms of which one's the new grid and which one is the old grid. Okay. So y from 1 to n minus 1. So these are the indices in our local grid. Okay. And here again we have n equals 6. So we have 6 elements over here. The elements that we actually own are, not including the ghost cells. So starting from 1 up to, in this case, index 5. Okay, so the periodic boundaries in terms of what the ghost cells actually represent, but we're actually computing is the new values for our own cells, which are between 1 and n minus 1. Other questions about this computation? Okay, so again, we've divided up the entire grid amongst the processes, which means that this is an iterative algorithm, right? And so between each iteration, we need to do communication of those, the neighboring cells, the ones that, again, process 0 needs the value of the element 12 from process 2 in order to compute the new value of element 1. And it also needs element 5 from its right-hand neighbor as well. So we need to have that communication be done between the iterations as well. Okay, so we will look at different ways of doing this communication using different UPC++ features. So we'll start off with RPC because we've already seen how to do RPC. And so essentially what we'll do is we have our actual grids are represented using global variables on each processor. So each process has its own global variable for its old grid and its new grid. And then we have a get cell function over here that is going to take in an index, and then it's going to just directly access the element out of the global old grid variable. Okay. And because it's just a regular function, it can actually refer to variables that have static storage duration. And so we can just access old grid directly over here. Now, the interesting thing is that we can do an RPC to our neighbor and have it invoke the get cell function. And that get cell function is going to run on our right-hand neighbor, which means when it runs on that neighbor, it's going to access that own processors, that process's old grid directly. Okay, so we're invoking this function over on our right-hand neighbor. That invocation is going to access the element on that right-hand neighbor, and then that value will be returned as the result of this RPC. Okay. So here we're invoking get cell, and then we're passing the index 1 over here. So index 1, if my right-hand neighbor is process 1, that would be the element number 5 over here. And so what I get back from this RPC call is a future of double. And then if I wait on that, then that actually gives me the double value itself. Okay. And then I can go ahead and, either store it in my own grid or just use the value directly. In the context of sort of a full iteration. So what we can do is, rather than doing the wait immediately, again, generally speaking, we want to be overlapping communications and computations. So rather than doing the wait immediately, what we'll do is we'll actually initiate the RPCs at the beginning of our iteration. And again, we get back futures for that. So in this case over here, essentially I've initiated those RPCs to obtain my 2 neighboring values over there. Then I can go ahead and do my local interior computation. I can't compute my boundaries because I need those ghost cells in order to do that. Okay, but I can go ahead and compute the interior while those transfers are happening. Okay, so here we are overlapping actually three different things. We have two RPCs that are being overlapped, as well as the interior computation of the grid. And then, once we're done with the interior computation, now we can't actually do anything else until we get those until those transfers have completed. So this is where we can actually call wait in order to compute our boundary cells. And in this case over here, we're just reading those values out of the features directly and using them rather than storing them in the grid first and then using them. But you could do it either way. So again, this illustrates that we can actually take full advantage of asynchrony to do this overlapping of communication and computation. All right, so this is an iterative method. Again, what the iterative method does is it swaps the grids at the end so that our new grid becomes our old grid for our next iteration, and then we reuse what used to be our old grid as a new grid for the next iteration. Now, one of the things that some of you may be observant and have noticed that if this is our entire iteration, and we're doing this across multiple iterations, we may run into race conditions. Okay. And again, what we can actually have is we can have some process, since we don't have any synchronization at all here except between processes. That means that our processes actually can get out of phase with each other. And so if I have one process run ahead of the others, when it does an RPC, it actually can read old data rather than the new data that it wants. Okay. And again, so this is one of the things that is a trade-off of one-sided communication, which is that it decouples the synchronization from the communication itself. Okay. Now, again, that can be a good thing because that means that we don't need to pay the cost. We don't pay the cost of the synchronization if we don't need it. But if we do need the synchronization, then we need to put it in explicitly. Okay. So again, just to reiterate what can happen over here, so we can have a processor get ahead or behind other processes, and then essentially the results of these RPCs. If my target is, let's say, 2 iterations behind me, if I do the RPC to actually read that value from that target process, then I'll get something that's actually a couple of iterations old, rather than from the current iteration. Okay. And the end result is a race condition, and what we need to do to fix this is actually to put in synchronization. Okay, there are many ways to do synchronization. For simplicity right now, we'll just do the naive, put in barriers. And so we'll put in barriers around the swap to ensure that both the RPCs from the current iteration and the next iterations are actually accessing the right data. Okay, now there are better ways of doing this synchronization, but for the interests of this exercise, we'll stick to the simple, naive way of doing it. What we've seen over here is that we can use RPCs to actually do this communication. Now, we don't really need RPC to do this because we're just reading data values, and essentially we're not moving computation really over to other processes. So a better abstraction in terms of a better way of doing this communication is actually through remote memory access instead, so RMA rather than RPC. Okay, so using RPC was more of an illustration of, this is what you can do with, this is something that you can do with RPC and how RPC works, as opposed to this is the best way of doing it. Okay, so again, in this case, we just need to move data, so RMA is a better abstraction for doing that. And UPC++ provides APIs for this as well. And again, I'll reiterate that RMA is the programming model feature, RDMA is the network layer feature, and RMA can be implemented on top of RDMA if it's available, which makes it very efficient. So in terms of the different RMA variants that UPC++ provides, we have rgit, which is short for remote git, does a git, initiates a git. And so there's two versions. There's the scalar version that just obtains a single datum, okay, and it takes in a global pointer that points at that object and retrieves its value. Okay, so that's scalar version. We also have a vector version. So looking at the bottom, we have essentially, rather than just passing it a single global pointer pointing at a single piece of data, you pass it a global pointer that's pointing at an array of data, and then a local pointer that's pointing at some local memory to copy in that entire array, and then a count of elements to copy, and it transfers that entire essentially array of data as opposed to just a single element. And similarly, we have scalar and vector versions of put. So for put, the first argument in the scalar version is the actual data value. Here we're just sending the value 42. And then the second argument is a pointer to the memory location where we want that value to be copied. Okay, so again, a global pointer. And then similarly, we also have a vector version that can copy an entire array of values. So we give it a local pointer to some local array, a global pointer that's referring to some array in the global address space, and then a count as well. Now, one of the things I want to point out here is that the scalar rgit is the only one that actually gives us a value as the result of the operation. It's whatever the value of that object is. So we get back a feature of int. For the other ones, for a put, we're moving a piece of data here, the 42, somewhere else. And so we're not actually getting a piece of data back, but we are still getting there's still a notification event that the transfer has completed. Okay, so we get an empty feature that represents that completion. And then for the vector versions, again, the data are actually read and written from pointers. And so what we get back is a notification that the operation is completed. Okay, so then let's take a look at sort of Jacobi using RMA. And it's actually going to take several steps to get there. One of the things that we got with RPC was that we didn't have global pointers at all. We didn't need to know where the objects lived on other processors, because that was essentially the RPC implicitly did all of that, right? We just sent sort of the getSelf handle to the getSelf function, and then the getSelf function just used local information to figure out where that data was and gave the data back directly. So for the RMA variant, we actually have to do a little bit more work to ensure that we know where the data actually reside on our neighbors. Okay. So also in these variants, we will actually end up using the space for the ghost cells as well. Okay, so if this is my rank that I'm looking at right now, essentially what I need is a pointer to my left neighbor's grid. And in fact, I need 2 pointers because there's 2 grids, right? There's the old grid and the new grid. Okay, but just for simplicity, we'll just look at a single grid right now. So I need a global pointer to the start of the grid on my left-hand neighbor, and I need another global pointer for the start of the grid on my right-hand neighbor as well. Okay. So if I have these global pointers, now I can actually do an RMA to actually obtain the data that I want. Okay. And so looking at the code down here, I have a local pointer to my own grid. I have global pointers to my neighbor's grids. Okay. And now I can do, a get if I'm initiating this, from rank 1 in order to obtain data from rank 0 and rank 2. I need to do a get. And in this case, since we have a 1D iteration, it's just a single datum that we need from each neighbor, we can actually use the scalar version. So we just give it the address of the element that we want. Okay. Now from my left neighbor, right, I need that 4 over there, which is at index n minus 2. Again, n was 6 over here, so this is at index 4. So what I can do is actually, I can do pointer arithmetic just like I could on a normal C++ pointer in order to, translate this pointer to be a pointer to that element over there, and then do a scalar get on that. Okay, similarly from the right neighbor, I need the thing at index 1. And so I can do pointer arithmetic to do that translation and then do an arget in order to obtain that data. And again, what we get back is a future, so we need to wait on it to actually get the actual result. Okay, for us to be able to do this, we need to have those pointers to our neighbors. The other thing that we need is that the grids actually need to be allocated in the global address space. Right. So again, this wasn't an issue when it came to the RPC version because we weren't using RMA over there. Okay, but now we're using RMA in order to actually do remote memory access. The memory needs to be in the global address space, which means it needs to be in the shared segment of the neighbor. Okay, so that means the data needs to be allocated in the shared segment. And the way that works in UPC++ is we actually provide our own templates for doing data allocation in the shared segment. A standard mu actually will allocate in the private segment, and instead you need to call these UPC++ templates in order to do allocation in the shared segment. Okay, so here we're using the new array function template. We also have just a new underscore to if we want to allocate just a single object. Okay, but here our grids are array, so we're using new array. We give it the element type that's double. We give it the number of elements, which was our n equals 6 in our running example. And again, we have 2 grids over here. We have the old grid and we have the new grid, so we do 2 of these allocations over here. Now, these allocation calls are not collective. So each process essentially needs to allocate its own memory by calling new array individually. And each of those allocations happens independently. And one of the things, again, we talked about previously that our design principle in terms of scalable data structures. We do not have a symmetric heap, unlike UPC. And there's several reasons for this. One of them is to avoid non-scalable data structures. Another is, to properly support subsets of processors like teams or similar to MPI communicators. So again, in UPC++, the allocations are individual. So what we need once we do our allocation is we need some way of actually communicating these pointers to our other processes. So we'll see that momentarily. Questions so far? Okay, so I do these allocations and I get global pointers back. Now I don't actually want to be doing my local computation through global pointers. Okay, essentially what that would be doing something like an arget to actually read it. And so that would actually impose some overhead in the library in terms of checking to see whether this is local or not. So essentially what we want to actually work on them locally is we want to take those global pointers and cast them down to local pointers. Okay, and so the global pointer template actually has a member function called local that actually does this. Okay, so essentially it strips away the affinity and just gives us a raw C++ pointer to that data. And of course, this is only valid to do if we actually have direct memory access to that data. Though, as we'll see later, if processes actually share physical memory, you can also do this too. Okay, so essentially after my allocation, essentially the next thing I want to do is actually get the local pointers out of it so that I can do my computations through local pointers as opposed to through the global pointer. A couple of questions. Does NeoArray work with heap allocated objects like GIMP's arbitrary precision numbers? And Dan answered that NeoArray T is a function template that works for any type T. NeoArray has the same effect on calling Neo and converting to global pointer. So the difference is, again, whether we're allocating in the private segment versus the shared segment. So if you just do new, you're allocating in the, in the private segment. If you do UPC++ version of new or NeoArray, then we're allocating in the shared segment. And we do provide means of just allocating raw memory, and then you can use placement new later on to actually construct an object in that previously allocated memory. Okay, so let's look at the full Jacobi iteration assuming that we've gotten the global pointers. Again, as we've talked about, we still do need to actually communicate these global pointers to everyone, but we'll get to that later. For now, we'll take a look at doing an iteration using these global pointers. Okay, so similar to what we did beforehand, we want to overlap the communication with the computation. So we want to initiate our transfers first, do essentially our interior computation, and then do our boundary computation at the end. Okay, so in this case over here, I'm actually using vector versions over here. You could use scalar versions since it's just a single element, but here I've chosen to use the vector versions because that's what you would do in, for more complex examples as well. Oh, sorry. So again, we initiate the argets. Since they are the vector versions of them, we get back just a feature that doesn't carry a data value, but that still sort of carries around the completion information. We do the local computation, and then we can wait on the left-hand transfer to complete, do the left-hand update, wait for the right one to complete, do the right-hand update. Questions on this? Shared segment pre-exists allocations then. So as Dan mentioned, the shared segment is created at startup. And we do have sort of an allocator underneath the hood that parcels that out using new and NeoArray. Other questions? So in terms of the size of the shared segment, that's something you can actually configure. One of the things that we see in this particular example over here is that essentially we're doing a wait and then we're doing the update afterwards. And I alluded to beforehand that you can actually attach computation to sort of a future to be executed when the future completes. And so rather than, doing this wait, essentially separating the transfer and the actual update, essentially we can use that then capability to actually put both of them together. So the way we do that is, we get a future out of this arget, and then we can attach a callback to that. And that callback will be invoked when the feature is readied, and it will be invoked on whatever data is encapsulated in the feature. Okay, so in this case over here, I have a lambda function, an anonymous function. This feature is an empty feature, so I have 0 arguments. Okay, so when this feature is readied, this function will be invoked, but because the feature doesn't contain any data, it's going to be invoked on no arguments. So therefore, it needs to be invocable on no arguments. And so then I am directly doing the update over here. And I will point out that we don't have any capture over here because new grid and old grid are global variables. And so therefore, they can be accessed without, they don't need to be captured from the local environment to be referenced over here. So we could also do this with the scalar version, which does produce a value. Okay, so in this case over here, I'm using scalar arget. That is going to give me back a future double. And so that means that the resulting function that I'm passing to then will be invoked on the double, namely the value that was transferred. And then I use that directly over here. Okay, so you can attach a callback to both an empty feature or a non-empty feature. For the non-empty feature, the callback will take in whatever values are contained in the feature as arguments. And I will point out that notice here in both cases, we got this empty feature as a result. And I want to point out that that feature is the result of the then invocation. It's not the feature that resulted from the arget. Okay, so the arget, we get a feature, then we call then on that, and that gives us back another feature that actually represents completion of, the entire thing, essentially. Okay, and since these functions inside here did not return anything, that's why we got an empty feature in both cases. All right, so this chaining of callbacks, allows us to actually, construct very complex dependencies between different operations. So, for instance, in this example over here, I have some global pointers. I do an arget to the source from the source, actually. Well, arget of data from the source. And here it's a scalar one, so I get back a feature of int. Then, without waiting for it, what I can do is I can attach a callback to actually use that int value and do something else over here. And here we're calling std_log, which will actually return a double. So we get back a feature of double over here. And then I can attach something else to that. So here what I'm doing is I want to essentially send the result of this out to this target location over here. So what I'm doing is I'm attaching a function that is actually going to invoke rput to transfer the resulting value over to the target. Okay. And one of the things to notice here is that rput returns a feature, then returns a feature as well. And the library is smart enough to essentially collapse those features. Okay, so I don't get a feature of feature, but I just get a single, a collapsed feature over here. And so if we look at the dependency graph, we have this on the right-hand side. We have an arget, and then we have a function that computes a log that depends on that value, and then we have a function that does an rput that depends on that value. And the nice thing about this is we only need to do a single wait. That essentially returns when the entire graph has completed. One other thing I want to mention is that, we sort of had a linear dependency graph in that previous example, but we can also have, sort of an arbitrary DAG, directed acyclic graph. And the way we can do that is there's a win all that essentially does the horizontal sort of constructing something that has a feature out of something that out of multiple other features. So essentially combining multiple dependencies into one. Okay, so conceptually like this. If I have something that depends on two argets, Here I have my two argets. I can combine them into a single feature that actually encompasses both of their values by calling winAll in them. And then I can attach something to the result of that. And because I have two pieces of data, this function takes in both of those pieces of data and can use them to do something else. And again, I can just do a single wait in order to wait on the entire graph. Okay, so putting this all together, essentially here what I've done is I do my two puts at the beginning and I can join them together using winAll. So I just get a single feature now that I can wait on. And the other thing that's different from the previous thing is I've done puts here rather than gets. Okay, but essentially I can do a single wait to wait for those puts to complete. Here I also have a, since I'm doing puts, I need to ensure that my incoming puts have also completed so that I can use that data. And so that's what this barrier does. And then I can go ahead and, do my boundary updates. We've looked at essentially how to use RMA and how to use advanced features of features like callbacks in order to simplify our communication and computation. One of the things that we haven't gotten to yet is that, we talked about how the global pointers need to be communicated between processes so they know where to actually, launch these puts or the gets that we saw previously, but we haven't actually talked about how to accomplish that. So that's what we'll do next. Okay. And our main abstraction for doing this is a distributed object. So conceptually, essentially, this is an object that is partitioned over a set of processes. That set need not be everybody, though by default it is. There's this second argument that's defaulted to all the processes, but that actually can take a subset of processes as well. And so what it looks like is that each process has its own local representative of this distributed object. And then you can also use this distributed object to access data from somebody else's representative. Okay, so in concept, if you're familiar with a coarray, it's similar to that. But there are several advantages that we have over coarrays. So probably the biggest is that we use a scalable metadata representation, as opposed to having essentially the metadata fully replicated on every process. We don't require a symmetric heap. There's no communication to set up or tear it down. And also we support subsets of processors. So just a simple example over here on the right-hand side, we have a distributed object whose element type is int. And, we construct it using a random number for each process. And so then what that looks like pictorially is that each process, again, it has a local representation, which is an int element on that process individually. And then through the distributed object, you can access somebody else's representative as well, as we'll see momentarily. So, again, the way that we can get everyone to actually have access to each other's grids is to actually place our global pointers in a distributed object. So construct a distributed object across all the processes that actually contains the grid pointers themselves. So let's take a look at that. What we have is here I'm introducing just a convenience alias. Again, this is a C++ library, so we can use nice C++ features as needed. So here I'm introducing pointer pair to be an alias for a standard pair of two global pointer of type double. And so then what I can do is I can construct a distributed object over a pointer pair. And each individual process has its own sort of local value. It provides the two grid pointers to its own grids. So it's old grid G pointer and new grid G pointer is what we called them previously. And so now we have a distributed object where each process has these 2 pointers as its own local representative. Okay, and so then how do we obtain somebody else's representative? We have this distributed object. We can invoke the fetch member function on it. We give it the process number of the rank number of one of the processes, and it actually obtains a copy of that value. And like anything else, we don't get the value back directly, we get back a future. Okay, so this invocation over here, this fetch invocation, actually gives us a future of pointer pair. And then when we wait on it, we get that pointer pair back. And then we can once again use fancy C++ to actually unpack it. But if you don't care for fancy C++, then we can also unpack it manually as well, as we see in this the code in the comment at the bottom. Questions on this? Okay. Now, one of the things that we do need is, so this distributed object, it must be constructed collectively, but that's not a synchronizing construction. Collectively just means that, the processes must all do this. But there isn't any synchronization in the construction. And instead, the fetch itself will actually essentially wait for it to be constructed on the remote end before we get the results back. On the other hand, we do need one piece of synchronization at the end over here. And the reason is because if the distributed object goes out of scope, then the local representative does get destructed. And so if we have some outstanding fetches, then that would actually end up being a problem. Okay, so here I've solved that by placing a barrier to ensure that nobody leaves this scope until everybody's done with obtaining their pointers. There's other ways to fix this. For instance, we could allocate the distributed object in heap memory instead, so that it doesn't automatically get destructed. So this destruction isn't tied to a scope. Okay, but again, because it's C++, we do need to be careful about destruction. And in the case of a distributed object destruction, it destroys the local representative. So again, with having the distributed object as a stack allocated variable, we need the synchronization at the end to avoid a premature destruction. But we don't need a synchronization between constructing the distributed object and invoking fetch. Okay. So, the reason is because, again, fetch gives us back a future, doesn't give us back the value directly, and that future isn't readied until the distributed object has been constructed on the target processor, and therefore the local representative exists, and therefore that value can be transferred over. Okay, so there is no synchronization needed between the construction and the fetch itself. So distributed objects are created locally but are exposed to the global address space through the dist object type wrapper. They aren't stored in the global address space. So in our current design, they are not. The underlying data is not stored in the global address space. But essentially, we saw in our first version of Jacobi that wasn't a problem for something like RPC. And so the way that fetch is actually implemented is using a similar mechanism as RPC. So it doesn't actually do an RMA. And in fact, again, in order to do an RMA, we need the synchronization to ensure that the object already exists. And so that's not something that we want distributed object to actually require. And so therefore, it's not using RMA. And that allows us to avoid the synchronization. Okay, so we've seen essentially now all the pieces for a simple 1D Jacobi implementation using either RPCs or RMAs. Again, with RMA, we need to allocate the grids themselves in global memory, we need some way of communicating those pointers, and the distributed object is what allows us to do that. So let's look at another example that's different than Jacobi. So it's the distributed hash table. And essentially what we want is we want a hash table that is partitioned across the different processes. Okay, so a distributed analog of something like std unordered map, where we support insertion and lookup. For simplicity in our presentation, we will assume that keys and values are of type std string. But essentially what we have is we have a collection of standard unordered maps among the processes. Okay, and then, essentially we determine through the key, like which partition that key value pair actually should be stored on. Yeah. So again, we have this partition where each process essentially has its own piece of this distributed hash table. And so that motivates using a distributed object for that, right? So that's exactly the abstraction that gives us, each process having a local representative. Okay, but what we will do is we will package this up into a, its own abstract data type, so that we don't, so that we can provide the appropriate abstraction for the distributed hash table as a whole. So let's take a look at that. So what I've done is I've implemented this distr map class. Now, if I were actually writing this in a real application, this would be templated on the key and value type. But as we said, for simplicity, we'll assume that the key and values are both string. Okay. And the underlying data representation is a distributed object. Okay. And what is the local representative of that? It's just a std unordered map with, in this case, string as both the key and the value type. Okay, so again, over here, all I've done is I've created a type alias. I haven't actually created an object. I've just created a type alias. As far as the object itself, that's this member variable over here. Okay, and here I'm initializing it so that my local representative is actually an empty unordered map. Now we'll use a sort of an owner compute rule where, an insert needs to go to the owner for that partition, and also a get, a lookup. We also need to know which process actually owns that piece, so that we can, send a message, an RPC to that process in order to actually do the lookup. And so here I've abstracted away the sort of figuring out who the owner is as just this very simple member function, get target rank. It takes a key and it computes which process owns that, and we're just doing a simple, compute the hash, standard hash of that key, and mod it by the number of processors to get the owner. Questions on this? Okay. So yeah, there was a comment that this cleared up the previous question about global pointers and dist objects. I'm glad it did, and I will sort of just point out for people who are still a little bit unclear. Global pointer just points to some piece of memory in the global address space, whereas a distributed object is something that's actually an actual object that is across multiple processes where each process has a local representative. So here we have the data representation again for our distributed hash table. It's just a distributed object with a local hash table underneath it as the individual local representatives. So then using that, we can now implement in, our, insertion and other operations. So our insert, it takes a key and a value. And again, what we want to we're using an owner compute rule. So what we need to do is we need to send it over to the owner of this key, of the partition where this key should be located, and have it do the insertion over there. Okay, and so this is where we now actually have some useful work being done in an RPC. Okay, as far as the target processor, we have our member function getTargetRank that actually computes that. And then we actually have the function that will be executed on that target. And this takes in several pieces of data. The first thing is that it will take in a reference to the distributed object. That's actually the data representation of our distributed hash table, and then also the key and the value. Okay. So what do we pass as arguments? We pass our own local representative. And what UPC++ does is it automatically translates that to the target's representative through this RPC. Okay, so we have our local representative. UPC++ sees that, oh, this is an argument to an RPC. It obtains the unique name out of this distributed object, sends over the name to the remote. On the remote, if it already exists, then the RPC can be executed. If it doesn't exist, then it's deferred until the distributed object is actually constructed at the remote. And then once it does exist, then that universal name is translated to that target's representative. And then that is what actually gets passed as the argument over here. Okay, so essentially here, LMAP is a reference to our target process's local representative. The keys and values, the key and value are passed as arguments over here. Now notice here that key and value are string. We do actually support transferring lots of standard library data types like string, and we'll get to that in more detail when we talk about serialization later. Okay, so those data values actually get transferred along with the, as part of the RPC. And so then we get copies of them here. And again, LMAP is a distributed object. We do have a dereference operator to get to the local, again, going from our distributed object to our actual underlying unordered map. Now here this doesn't do any communications. This is just looking at the local representative. And then we can index into that with the key and then store the value as the corresponding value for that key. Questions on this? Does RMA work for strings? No, it does not. So RMA only works for things that can be byte copied. And strings are a variable size, so no, they can't actually be byte copied. Okay, so we can also look at find, which is similar. The main distinction between find and insert is that find actually produces a value. So actually, let me go back just for a second. Now, going back here, we return the result of the RPC, and so that's an empty feature. Whereas for find, we're doing an RPC and returning the result of that again, but now we actually have the actual value, a feature representing the actual string value. Okay. So as before, we've figure out who the owner is, and then we send over this RPC. And as before, we have our local representative of the distributed object that gets translated over to the target's local representative. We have the key as well that we're passing as the argument. Okay. And then what happens on that target is that it can look up to see whether or not that key is in its unordered map. And here we're using the arrow operator, whereas before we did start a dereference, but here since we're calling a count member function, and we're doing arrow to do both the dereference and the member lookup. And so again, that dereference will get from our distributed object to the unordered map, and then we're invoking the count member function on that unordered map, and it tells us whether or not this key is in the map. If not, we'll just return some, some nonce that tells us that it's not in there. Otherwise, we'll actually obtain it out of the unordered map. And again, here we're using the dereference operator to get from the distributed object to the unordered map, and then using the square brackets to look up the value of the key. The question: if one processor runs insert and another runs find, could find end up with an inconsistent result? Well, I mean, so that would be a race condition, right? And so then it's up to the application whether it cares whether that's a problem or not. In something like meta hitmar, essentially you have different phases. You have insertion phases, and then you have read phases afterwards. And so there is a synchronization between the insert and the find. Just some results in terms of implementing a distributed hash table. These are results from our IPDPS 19 paper, which you can also find on the UPC website. We did a weak scaling experiment up to 32,000 cores. The implementation is a little bit more advanced than what we saw in the slides. So a couple differences. We used, rather than using strings, we used a fixed size char arrays as our values. And also, we didn't use only RPC like we saw. We actually have a combination of RPC and RMA. So essentially, this implementation that we see over here actually does an RPC to construct a landing zone. So our value, instead of being the actual value itself, ends up being a pointer to the value. And so an RPC is done to actually allocate memory, and then an RMA is done to transfer the actual value over. And so that is more scalable for larger element sizes. So what we see here is that the combination of RPC and RMA actually does result in reasonable scaling. And what you see here is the different element sizes. Later on, we'll also talk about meta hitmar, which actually, again, uses a more advanced version of this distributed hash table as well in a real application. Okay, so just to give you an overview of what we'll see for the rest of today, we're sort of transitioning to more advanced sort of aspects of UPC++. We don't have time to go over them in any detail, but we do just want to give a high-level overview of sort of some of the more advanced features of UPC++. And then we'll also, spend a few minutes talking about some applications that have been written using UPC++. So one of the things that came up before is sort of essentially, when does an RPC actually happen on the remote? When does it execute on the target? And so sort of the core question there is, what is the progress model of the library? How does the library, how do things actually get done? How do asynchronous operations actually get executed in UPC++? So a reminder of what an RPC actually looks like is we have the initiator injects the RPC. We have a handle to the function, and the arguments get transferred over to the target. They get enqueued on the target, and at some later point they get executed, and that later point is determined by the progress model. So the most important thing about the progress model in UPC++, actually before we talk about that, one more thing I'll mention is that after it executes on the target, the result, if any, or just the completion notification gets sent back to the initiator. And then there's also sort of, when does that future become readied? And again, that's also something that's controlled by the progress model, is when does this notification happen on the initiator? So there's two different things that essentially have to do with the progress model. There's when does the actual RPC execute, the function execute on the target, and then when does the notification happen on the initiator? So one of the things that's fundamental to the design of UPC++ is that we do not implicitly spawn our own threads to advanced communication or asynchronous computation. And this design was motivated by both efficiency, by keeping the runtime lightweight, avoiding internal synchronization, and also as part of the programming model. So one of the things that you can do, so just the question that was just previously asked in the chat about one process running insert and the other one resulting find. Could he end up with an inconsistent result? So because it's an RPC and they're executing on the same target, they're going to execute one after the other. Now, without the synchronization, you don't know whether the insert will happen first or whether the find will happen first, but they won't happen concurrently. It's not like you'll get some inconsistent state inside of the unordered map itself. Okay, you either get it's there or it isn't. And so this means that our insert and find don't actually need to do synchronization internally. If I have multiple inserts, those RPCs again get run in series, one after the other, and we don't actually need to do obtain a lock in order to actually get exclusive access to the unordered map. So again, this was one of the motivating factors for our design decision in terms of no hidden threads, so that the synchronization both internally and also at the application level can be simplified. Now instead, the runtime relies on the application to invoke a progress function. And there's two levels of progress. There's internal progress, which advances internal state and sort of, does data movement, moves data along if it can be done so, but does not notify the application that, something happened. So it doesn't ready any features or do any callbacks or anything like that. So what does do that is user level progress. So that's what does things that are visible to the application itself, like making a feature ready, like invoking a callback, or invoking an incoming RPC. Questions so far? Okay, so how does progress actually get invoked? Sort of the main API for that is actually a progress function that you can call directly. However, it's also called indirectly through anything that's blocking. Okay, so what are things that are, what are things that are blocking? We have wait. Here we go. We have wait that, waits until the feature is ready. So that's a blocking call. And, for things to actually end up being ready, we actually need progress calls. Otherwise, things won't end up getting ready. So wait underneath the hood calls progress. And so does barrier, which is also blocking. Okay, so these do actually invoke progress. So in many applications, you don't need to invoke it directly. And in fact, in all the examples that we saw so far, we didn't need to invoke it directly. When you do, when you need to invoke it directly is when you're expecting callbacks to happen or remotely invoked RPCs to execute, but you're sort of inattentive. So for instance, if I have some big computation loop, I may want to put some progress calls in the middle. If I have either local callbacks or I have incoming RPCs that I need to get invoked. Okay, so in some applications, you might actually need explicit calls to progress, but in many cases, you don't. So what does progress actually do? It invokes some number of outstanding, received RPC functions or .then callbacks. And that some number could be 0. So, it may need to actually be periodically invoked. Now, because of the progress model, sort of what we have in terms of limitations on callbacks is very minimal. It's a callback itself. You can't actually have a blocking call inside of it because that callback is already running in progress. And so, the code inside the callback itself shouldn't do something like call, wait, or bury. Okay, but it can initiate an RPC or an RMA or even an asynchronous barrier, something that isn't blocking. Moving on to some more advanced features. We do support atomic operations that utilize the network hardware if it's available. So for things that do require atomic updates, remote atomics can be more efficient than, say, using an RPC to do the serialization. So in UPC++, the sort of abstraction that we use is that we have atomic domains which are defined over sets of atomic operations. Okay, so essentially what you do is in your application, you figure out, okay, what are the atomics that I need? So in this case, we have load, min, and fetch add are the three atomics we need for this application. We construct a domain over that. We also have a data type. And then what the library does underneath the hood is it looks and checks, is this set of operations on this data type supported directly in the network hardware? If so, it will end up using network atomics. If they're not fully supported on the network hardware, then it will end up using some CPU-based atomics instead. Okay, so essentially what this guarantees is that for whatever set of atomic operations you have, you get the best performance out of it. And then in terms of actually doing operations, what you do is you call one of these operations on the domain and you give it a global pointer to the piece of data that you want to be accessed atomically. Okay, and again, even though it's atomic, it's still asynchronous, so you get back a future. In this case, the result of the fetch add. Questions on this? Okay, so we talked about previously that strings can actually be transferred through RPC. And so we have a more sort of full-featured version of serialization. And here, I want to clarify that the term serialization is overloaded in computer science, right? So what we were talking about before in terms of things executing serially, that's one form of serialization, avoiding race conditions. But here, by this serialization, we mean converting the data into bytes, shipping it over, and then reconstructing the data on the remote end. Okay. So UPC++ has full feature support for serializing complex data types. So for things that can be byte copied, it just byte copies them, and there's no overhead of any translation. It's just whatever the transfer. But for more complex types like string, like vector of element types that are also serializable, and we can actually have this complicated nested type over here. We have a vector of a list of a pair of int and float, and since int and float are serializable, they're actually byte serializable. Then we have pair on top of that. That's a standard library type that we support serialization for. List, we also support. Vector, we also support. So this entire thing we support. And, we do the hard work of translating this to the byte representation, sending over the bytes, and then reconstructing it on the remote end. Okay, so this works with RPC. There was a question beforehand in terms of RMA. RMA just does byte transfers. Okay, so RMA will work for char int double or, C compatible, standard layout types. But RPC supports more general things as well, including things like vectors and strings, and we also support user-defined serialization. So if you define your own types, you can also define how serialization works on that type. Questions on this? All right, now there is a cost, of course, associated with both the serialization, converting it to the byte representation. Then there's a transfer, and then there's converting it from the byte representation on the target back to the original sort of data type. Okay, but oftentimes, if the function that we're RPCing over actually just processes the data directly, it doesn't necessarily need to actually reconstruct an entire, complicated type as a result. And so we also support, a special sort of more efficient way of doing serialization over a container that's called a view. Okay, so essentially this is a non-owning sequence of elements. The way that it works is that if you have some sort of container, rather than passing that directly to an RPC, what you can do is you can construct a view over this. And so down here, that's what make view does. And all this does is it obtains the begin and end pointer, and that's that's what the view is. So here we're constructing it directly from the container itself. You can also construct it from your own begin and end iterators, say if you wanted a subset of that container. And so this view is what gets passed to RPC. And here I'll mention that this is a variant of RPC. RPC FF is another variant that doesn't actually return a notification. It's not super important, but I just want to point that out because it is being used here. So what do you get on the remote end? You get a view over float, but this does not necessarily construct a vector on the remote end. And in fact, in this particular example, what you're going to have is the floats will actually live in a network data buffer, and they get operated on directly in the RPC. And once the RPC itself is done, then the network buffer is reclaimed. So a vector is actually never created on the remote end, and we don't actually have to pay the cost of doing that construction. Okay, so again, this is a situation where the data is consumed directly in the RPC itself, and therefore you don't need to reconstitute the data structure on the remote end. You can just operate it on directly in the network buffer. I will make a forward reference and say that we will see this this is actually used. We'll talk about how it's actually used in sparse solver, in one of the sparse solver examples that we'll see later. One of the things that I briefly alluded to beforehand was that you can have, even in the distributed realm, you can have multiple processes actually share physical memory. And the reason is because our supercomputers, our systems aren't flat. Right, so we have, cores that live in a socket. We have multiple sockets in a node, and then multiple nodes, arranged hierarchically in switches, cabinets, and so on. Okay, so we do support some of this hierarchy. We have an intermediate layer that corresponds to processes that share physical memory. Okay, and so this is we use the team abstraction, which is our abstraction for processor subsets. And we have a local team that corresponds to the set that actually shares physical memory. And so amongst the processors in a local team, the shared segment is actually, the shared segments are actually directly addressable using load store access. Okay, so down here, I have a pictorial representation of 2 nodes, and each node has 2 processes that actually share physical memory. They do have their own shared segments, but these segments are directly accessible by, process 2 can directly access process 3's memory and vice versa. So what this means is that we can avoid, network communication as well as copies by taking advantage of this hierarchical organization. So previously we saw that we can, if we have a global pointer, to something that lives in our own memory, we can downcast that to just a regular raw C++ pointer. But we can also do that if we have a global pointer to something that lives in another process's shared segment, if that other process is in our local team. Okay, and we can take advantage of that to essentially build data structures that avoid that minimize replication. So here what we have, again, we're the same situation as before. We have 2 processes per node, and rather than allocating a data structure, excuse me, rather than allocating a data structure on each process, we can just do 1 per node. And in this case, we've arranged for it to live on the process whose rank is 0 in the local team. So 0 with respect to the node. And so the actual code to do that is we first have to, figure out what our ranks are with respect to the local team. So I can call rank me on the local team to figure out what is my rank in my local team, and also rank n to figure out how many processes are in the local team. And then if I am 0 in my local team, then I can do the allocation. And then I can send that over to everybody else in my team. And so we have a collective operation over here. We don't have time to talk about the full set of collectives that we support, but here we have a one-to-all. But we can actually do this over just a team itself rather than over all the processors. So this sends, the pointer to this array over to everybody else in my own local team. And then once that's been transferred, everyone can downcast it to a local pointer. And again, because all of the processes in this local team share physical memory, this downcast is actually valid. And so then we end up, as we see down here, everyone has a local pointer to this actual thing that lives in process 0 on this local team. And then they can just access it directly through, direct load store. And here, using square brackets to index directly into it. Questions on this? So what this gets us is, there's several different things that we get out of sort of this, taking advantage of this hierarchy. The thing that we kind of saw here is that we can avoid replicating data across different processes in a local team. We can, have just 1 copy per node as opposed to 1 copy per process. So for something like KNL, where we might have 272 processes in a single node, that's a huge win. But the other thing is that, because we have load store access, that means that we avoid communication and also copies. So, doing an RGET, for instance, not only does it, have to actually, there's a sort of branch inside of it to check, do I have local, can I access this directly? But then it also makes a copy. We get it by value. So if I just use direct access to it, then I can actually avoid that copy as well. Okay, so we avoid communication overheads, we avoid copies, both in terms of data storage as well as, time. Questions on this? All right, a few other things. We sort of talked about features extensively. We talked about sort of being notified when the operation as a whole has been completed. But we actually have a very rich sort of feature set when it comes to operating with asynchronous, interacting with asynchronous operations, as well as, when, we get notification. So features are one way of interacting with asynchronous operations, but we have other things like promises. We actually already saw callbacks as well, and That's another thing that we can, another way we can interact with asynchrony. The other thing is that we can actually give the application access to other sort of intermediate completion steps as well. So things like, when is the source buffer, if I have, say, the source buffer of an output, when is it acceptable to modify that buffer? And that's typically some earlier point than when the transfer is completed. And so we can actually provide notification to the application of these intermediate steps as well. So just a couple of examples of how we can use more advanced forms of completion. So one of these is that we can use a promise to count the number of outstanding operations. So previously we saw a kind of naive example of storing a bunch of futures inside of a vector, where we had a bunch of different operations that we wanted to track. But we can actually do this more simply with a promise itself. Okay, so conceptually, a promise represents the producer side of an asynchronous operation. And when you do a UPC++ communication operation, it implicitly creates one. However, you can instead provide your own promise, and then it will use that as the producer end. Okay, so looking down here as an example of doing that, we create a promise, our own promise, and then we do our gets, but rather than having it create its own internal promises, we pass in that promise for it to use. And then when we're done initiating these RGETs, we can actually obtain a future out of that promise to get the consumer end of it. So we have a single future that now represents completion of a whole bunch of these RGETs. And so then we just have a single thing to wait on. Right. One more interesting example of completion is that we can actually do something that we refer to as a signaling put, which is essentially attaching some computation to an RMA operation. Okay, so here what I'm doing is I'm doing a transfer from some source to some destination global pointer. And then I'm attaching sort of a completion operation to run on the remote end after the transfer has completed. Okay, and so essentially here it's just consuming whatever was transferred. So, this, again, it does an RMA put, essentially informs the target upon the arrival by enqueuing this RPC as a result of that, and then the RPC can, do some updates on the end as a result of that. And so what we end up with this combination is something that looks kind of like message passing, because we're combining a data transfer with some sort of operation on the other side that can do synchronization or do some update. But even though this kind of gives us an abstraction that's similar, that can accomplish things similar to message passing, it can still do this significantly more efficiently. Okay, because the initiator, again, specifies all the metadata. So how is it different to rput and then .then? Now, .then enqueues something to be done locally. So what you would need is an rput .then and then have an RPC be launched inside of the .then. Doing that requires the rput to complete, so that's an entire round trip. And then it launches the RPC as essentially a second round trip, as opposed to, this rput with the RPC as the completion. It can oftentimes just do it in a single message. And even if it can't do it in a single message, it can actually transfer both the RMA and the rput concurrently, as opposed to waiting for one to complete before the other to be done. Other questions? Okay, so I'll just briefly mention a couple of other things. We do support memory transfers between GPU and CPU memory, and both between local GPUs and local CPU memory, as well as remote GPUs as well. And in fact, any combination of local and remote CPU or GPU memory. And we also have support for non-contiguous RMAs. So we saw the simple example of 1D Jacobi for multidimensional, nearest neighbor computations. The ghost region isn't necessarily contiguous, and so we do have support for several different variants of non-contiguous RMA as well. So in the last few minutes, I'd actually like to talk about a couple of application case studies of using UPC++. So as we talked about previously, it's been used in several different applications and application proxies. The two that we'll talk about today is we'll talk about sparse solvers to begin with. And in fact, we'll first talk about a proxy for multifrontal sparse solvers, and then we'll talk about it being used in SymPack, which is in a separate solver for sparse symmetric matrices. And then we'll also talk about UPC++ being used in MetaHitmer, which is a genome assembler. So, question: can one do arithmetic on global pointer? Could that end up in some remote segment? So you can do arithmetic on global pointer. In fact, we did that back in our Jacobi example, where we had a pointer to the beginning of a grid, and we did arithmetic to get to an element in the middle. Now, could that end up in some remote segment? No. Doing arithmetic doesn't change the affinity of the global pointer, but it just does arithmetic on the local address that's encoded within the pointer. So it doesn't, change which processor it's pointing at. So coming back to the application example, we have, our first motif is sparse multifrontal solvers. And so the sort of proxy is for an extend add operation, which is an important building block for these solvers. And so essentially what we have is we have sparse matrices that are organized in a hierarchy with parent-child relationships. There's computation done in the child matrices, and then those results need to be transferred up to the parent. Now, these parents and the children actually can be distributed differently. So this involves communication. And in fact, the background colors here actually represent which process actually owns them. The parent actually happens to be distributed amongst 6 different processes. Then our left child is distributed amongst 2 processes, and our right child is amongst 4 different processes. So again, what essentially happens is that once the left child or the right child is computed, we have the contribution block that needs to be communicated to the parent as part of this computation. So we did work with details in the IPDPS 19 paper. One of our collaborators did this work of doing this proxy application, comparing a UPC++ version of this communication pattern with 2 different MPI variants, one that does an all-to-all and another one that does point-to-point. And for the UPC implementation, essentially what it does is it constructs a view on a per sort of source and target process basis of the elements that need to go to a single destination. Okay, so we have these ones over here are going to go, to the same process, that gray one over there. Okay, so the code actually constructs a view over that and sends it using an RPC. And then the RPC itself, as part of the function that's being invoked on the remote end, actually unpacks them and moves them to the right locations. Okay, so this is an example of using both view and RPC to do this transfer. And here we have comparison for a for a specific matrix from, I believe this is from the suite sparse matrix set. And what we see is that, here we have UPC ++ at the bottom. Of course, lower is better. And we have up to a 1.79x performance improvement over the green, with the round dots, which is the lower one for MPI at scale, and that's the all-to-all MPI. And this is just one matrix example, but it's actually typical of the other matrices in this set as well. Yeah, and so this is on the Haswell partition of Cori, and then we see something similar for the KNL, the Knight's Landing partition there as well, where we see similar speedups as well. So again, that was the extend add operation, which is a component of these multi-frontal sparse solvers. We also have work. One of our collaborators actually ported another sparse solver to UPC++, and that's SymPack, which is specifically for sparse metric matrices. And this uses a combination of RPC and RMA in order to do transfers and computation. Okay, so essentially the updates are divided into tasks, and those tasks have various different data dependencies, and we can use future and future chaining and win-all to actually combine those, construct those dependency graphs. And when a dependency is actually satisfied, an RPC FF is done essentially to notify that the data is available. And so that sends a global pointer to the data, and so then the target can actually do an RMA to actually obtain the data from the processor that owns it. And the data movement is actually done using RMA, using RGit. And then when all the dependencies for a task are satisfied, it's moved to the ready list and then eventually gets executed. Okay, so again, we have a combination of RPC and RMA being used over here and global pointers in order to do the data transfer for this application. So there's actually two different implementations of this. There's a 1D distribution implementation and then also a 2D implementation as well. And the important thing for the 2D distribution is that it has a much finer granularity task graph, which means more fine-grained communication. And as we talked about at the beginning, that's one of the motivating use cases for UPC++ and PGAS. And so we see that, despite, or maybe because of this more fine-grained task graph, we end up with a significant speed up between the 2D and the 1D distribution. And then comparing this to a different solver, state-of-the-art solver, PastTeaks, we see that we have significant improvement for the new 2D version of SymPack. So here we have close to a 2x, a 1.85x improvement of the 2D SymPack over PastTeaks. And then for a different matrix over here, we have a 2.13 speed up. And in this one, actually, the 1D does better than PastTeaks as well. So to summarize, in terms of how UPC++ has been used effectively in sparse solvers, we see that we have this combination of RPC and RMA allows for simple notify system that data is available, and then that can be transferred using RMA. We also have SymPack actually does have MPI in it as well, and so that demonstrated interoperability between UPC++ and MPI. And all of the UPC++ design decisions and features lead to lower communication overhead, better overlapping, better use of asynchrony, more fine-grained tasks, and an overall better result. The simple distributed hash table that we did, isn't perfectly suited to MetaHitmer, and that's because it benefits significantly from larger messages, and so essentially needs aggregation, as opposed to completely fine-grained updates in the distributed hash table. And so in this graph, what you see essentially is latency compared to message size, and latency does get longer as message size gets bigger, but on the flip side, sort of the increase in bandwidth essentially outweighs that. And so the latency can actually be hidden by the asynchrony, whereas sort of the bandwidth is something that benefits significantly from larger messages. And so in order to actually obtain that higher bandwidth, what MetaHitmer does is actually uses a variant of the distributed hash table that actually does aggregation as well. And so what that looks like is that rather than sending out the RPCs individually for each update, it essentially has application managed buffers. And what I'm illustrating here is a single buffer per outgoing process. But there's actually variants of MetaHitmer that actually do buffers on a per node basis and take advantage of the hierarchy features in the shared memory bypass in order to even get better results. So the updates get aggregated until a buffer is full. And then when the buffer is full, an RPC is done to the target process. The RPC sends a pointer to the buffer. It doesn't actually send the actual data. And as with SIMPAC, what we have is the RPC essentially notifies the process that the data is available, and then the target process does again in order to actually obtain the actual data. So programmatically, though, this doesn't look that much different from what we did in terms of our distributed hash table. Essentially, their version of a distributed hash table, which they call, aggregated store, it actually, instead of doing an RPC directly in an update, it will actually buffer them. And then when the buffer is full, then it will send an RPC. And also when all the updates are done at the end of the phase, then the application invokes flush updates, which sends out all the data that has been buffered but not sent out yet. But again, programmatically, in terms of the data abstraction of this distributed hash table, it looks very similar to what we had beforehand. And as before, it's built on top of a distributed object. So some sort of high-level observations from this MetaHitmer implementation of UPC++. And also, I should give you some background. Beforehand, MetaHitmer was written using UPC, a combination of UPC and MPI. And so it's actually being translated over to UPC++. And so they found that, even just the conversion to C++ itself was a big win, because of the support for C++ features like templates, allowing for efficient code reuse. They make use of distributed objects, just like we did for distributed hash table. And what they've seen essentially with their sort of one-sided, RPC and then do arget communication, as opposed to all-to-all exchange in the previous MPI implementation, was actually a 5x improvement at scale in terms of performance of that communication. And they make use of, many different features of UPC++, including chaining features and constructing DAGs of features, RPCs that send other RPCs, sending by node and then by process. So I mentioned, they have a variant that does per node buffers as opposed to per process buffers. And so that's another optimizations that they put in there. And they've also made use of more advanced completion, things like promises. All right, then to summarize, we've seen again, a couple of application case studies where UPC++ has led to better performance and also better productivity as well. Especially in the case of MetaHitmer with being able to use C++ and also being able to match the UPC++ abstractions to what they're doing in the application itself. Just some concluding remarks. This has been just a brief overview of UPC++. We're a full-featured library. We didn't have time to go over to spend a lot of time on sort of more advanced features, but we do have resources that go into more detail. So we have a specification, a formal UPC++ specification. We also have a programmer's guide as well, and links to various UPC publications, such as the IPDPS 19 publications that we talked about. Various links to partner projects and optional extensions. And also, we do have videos and exercises from past presentations as well, including full presentations of the application case studies. The two things that I talked about in terms of sparse solvers and MetaHitmer. That's all I have. I very much appreciate all of you attending and all of your participation.
Well, I want to thank you and your team for presenting and answering questions during the presentation, and all the attendees who join our May developer sessions. Thank you.
So thank you everyone for attending, and thank you to ALCF for hosting and Yasaman for arranging all of this. Very much appreciate it.